Thank you, Jay. We'll hear now from Dr. Miskoczci, right?
Ladies and gentlemen, in this talk, we are going to go a bit deeper into the physics of the planetary greenhouse effect, and at the end we shall show that based on some new theoretical development and some simulation results, the greenhouse effect on the Earth has nothing to do with the global warming.
You're going to have to speak.
Yes,
Hold the microphone.
even closer. Yes. So these are the topics we are trying to cover, and then let us jump into immediately the first slide. The general view of the greenhouse effect is presented in this left figure, which was taken from a lecture note at the Columbia University, which is saying that if there is greenhouse gas in the atmosphere, then there is a returning long-wave radiation which is contributing to the surface net radiation and then warming up the surface. And then part of that obviously will escape, and then the net result is a warmer surface. The problem with this kind of explanation or model is that here the atmosphere is assumed to be completely opaque, which is not true, and the atmosphere itself is not homogeneous. In 1916, Eddington was giving us an equation for an atmosphere which has optical thickness inside, and then he was saying that the temperature is changing in an absorbing media linearly with its optical thickness. And this equation here is the solution of the radiative equilibrium equation right here. And 6 years later, Arthur Milne come up with an idea that let us use this equation for the Earth, and then let us assume that the assumption of infinite thickness involves little or no loss of generality. So he ended up with these two equations here, which is saying the upper one that this much is the air temperature at the ground, and this is the ground temperature, and both of them are changing linearly with the optical thickness. And then if you see a kind of a radiative forcing assessment in the ICCP reports, then you should think that these are all a parameterized form of these two equations. So we should say that these solutions are mathematically incorrect. And unfortunately, in the last 80 years, these equations are appearing in hundreds of articles, and then in astrophysics monograph and everywhere, and nobody ever bothered to solve this differential equation properly, get the proper B0, and then find out how the things works in a bounded semi-transparent atmosphere. So to see what is going on with these fluxes, obviously you have to do some computations, and then in the next slide, what we wanted to do, we wanted to see what is the global picture. For this, you need a global average temperature structure, water vapor structure, so a representative global average profile. What we did, we selected a radiosonde database called the Tyros Initial Gas Retrieval Database, published by Sedin and Scott in 1983. You will need a processing line by line and accurate code which is able to reproduce the interested flux terms, and then you need a spectroscopic data set to put in the code. This distribution of the radiosonde observations are not homogeneous in spatial and time, so you have to apply a kind of homogenization. And then what we did, we just grouped the profiles into 11 group, 5 latitudinal and 3 seasonal group, and we end up with a global average profile for which we computed all those involved fluxes, what we are interested in. The next figure is showing some standard Martian temperature profiles, and then absorber amount profiles. And then we also repeated the calculations for the Martian atmosphere, because if greenhouse effect is going on there, there should be a general theory which is explaining both on the Earth and the Mars. So the first simulation result is, this is the spectral flux density distribution for the global average tiger. We call this tyrosinus gas retrieval profile set tiger, and then this is the surface temperature dependent spectral flux density. And then we compared the computed flux densities for the US standard atmosphere. And then we just recognized that the individual flux term, the outgoing long wave radiation, the upward atmospheric emissivity, the transmitted flux density, the downward emissivity, the surface upward flux density, and the atmospheric absorption are different in these two so-called global average profiles, but still the greenhouse factors, which is 128 and 130 in the two cases, and the normalized greenhouse factor is just the same. So we started not to understand what is going on. How come that our profile, which is having 2.6 precipitable centimeter water vapor, and the US standard atmosphere has 1.26 precipitable centimeter water vapor, has the same greenhouse factor? So what is this greenhouse factor about? It's supposed to represent the greenhouse gas content of the atmosphere, and apparently it is not. So the next slide will show how the individual fluxes are depending on each other. Like we plotted the absorbed upward flux density as a function of the downward emittance, and the upward atmospheric emittance as a function of the surface upward radiation. We recognize that there are two practically straight lines with good correlation, and then one is saying that the total absorbed upward flux density from the surface is equal to the downward emittance of the atmosphere. The other is saying that half of the surface upward flux density is equal to the upward atmospheric emittance. Gentlemen, these are accurate line-by-line, most state-of-the-art computations of the individual profiles. And then we identified these two results as the Kirchhoff law, which is saying that if two systems are in thermal equilibrium, then the absorbed and emitted radiance should be equal. The other can be traced back to the virial theorem, which is saying that the total gravitational potential energy is equal to the kinetic energy of the half of the, so the double of the kinetic energy of the system. So these two findings, with this, we actually started to build a new greenhouse theory, which we shall see later. Next slide, I will show you what is going on the Mars. If you accept the Kirchhoff law, that implies that somewhere at the atmosphere there should be a level where the downward emittance is equal to the outgoing long wave radiation, and that thing theoretically must pick up the global average absorbed solar radiation. And then this is demonstrated on this figure. If you put a layer somewhere here about 2 kilometers, and you compute the OLR and compute the downward radiation, it will be equal at this point, pointing to the global average absorbed solar radiation. If you know this number, and you know the temperature, the source function at this level, immediately you can come up with a cloud cover, which is 0.6, which is actually realistic. So let us see what is going on the Mars. The Martian atmosphere is very weak, and then the global average outgoing long wave radiation transmitted atmospheric upward, surface upward, and the atmospheric downward are this. At this profile, the surface half of the, 2/3 of the surface upward radiation is much smaller than the OLR, unlike in the case of the Earth and the US standard atmosphere. So again, what the what the greenhouse factor is for, because this is a kind of greenhouse equation which is telling that if this much is the planetary effective radiance, then this much should be the surface temperature. So if this is not working on a Mars, it's working on the Earth, but it's working similarly for two absolutely different profiles, then what is the real physics behind? The difference between the two planetary atmospheres is plotted here when we plotted the surface upward radiation as a function of the transmitted radiation for the Mars and for the Earth. Apparently, in the Mars, you have a linear relationship, and on the Earth, it's a kind of saturation curve with a scattered dot. So the broadband radiative transfer scheme of the two panels are totally different. So with this background, we started to work on the theory, and then we write up the balance equations for the system, which first, the Kirchhoff law saying that the absorbed radiation in the atmosphere is equal to the downward radiation. Based on this equation, immediately from a balance equation, turned out the upward atmospheric emittance has nothing to do with the absorbed surface radiation. All of it is coming from the absorbed solar, the convective and other non-absorption related fluxes, and the planetary heat flux absorbed in the atmosphere. The second conclusion of the Kirchhoff law is that the greenhouse factor, which is supposed to be the trapped energy in the atmosphere, is equal to the difference between the downward and upward emissivity. And then based on this equation, we can write an energy conservation equation where the two opposite fluxes, the sum of these two is equal to the total solar absorbed radiation. We also set up or built in the theory, the virial theorem. The relationship, what we see is the SU equal 2 times EU, and then we end up a general relationship between the surface upward flux, the transmitted flux, the downward flux, and the OLR. And then based on this equation, we derived 3 different greenhouse factors, where the first is a constant 1/3. At this point, we were happy because that 1/3 is just fitting our picture that the Tiger global average profile and the US standard atmosphere just has an independent greenhouse factor on the greenhouse gas concentration. So this is a strange result, and this is pointing to a special structure of the atmosphere, which is, we shall see later, which is called the equilibrium, that radiative equilibrium atmosphere has this kind of greenhouse factor. The general equation will result in a greenhouse factor in this point, the G0, where the A is the absorption and 2A/5 is how the greenhouse factor is depending on the absorption. For weak or thin planets, you can omit this ED/10 terms, and you end up an equation which is valid for the Martian atmosphere. So the next question was that how come that the greenhouse effect is not depending on the atmospheric absorbers in this case? The solution is that if we go back to the equations of Eddington and Milne, that this B0 was incorrectly interpreted and was computed without observing the real boundary conditions of the system, which is the total optical thickness and the surface upward flux or surface temperature. If you solve this equation with this boundary condition, you are getting a B0, which is a pretty complicated mathematical expression, which you can simplify a bit if you introduce the transfer function like this, and then you end up with the general greenhouse equation, which is containing all the necessary boundary conditions for the system. If you apply the energy minimum principle, you will end up with a function that the surface upward radiation is the OLR divided by the transfer function, where the transfer function is this expression, and then this is depending on the total atmospheric flux transmittance. So then we end up with the surface temperature of this formula, which is totally different from Milner's suggestion. You see that the greenhouse effect or the surface temperature is not linear in tau. It is also depending on the total atmospheric flux transmittance. And then you should immediately note that these two terms are working against each other. When the transmittance is increasing, the optical thickness is decreasing. So this equation immediately reduces the sensitivity of any greenhouse gas perturbations, and then actually this is the right equation to use for an atmosphere in radiative equilibrium which has the given boundary conditions. The next is how the minimum principle works. The transfer function is depending on the optical thickness as these curves are showing. The global average B0, which is the integration constant of our differential equations, is picking up the maximum of these curves in this case, not in the US standard atmosphere. So when an atmosphere is in radiative equilibrium, then the optical thickness must be a given value which is at the maximum of the the flux transmission function, the F. And then this is valid also for areal averages like the Arctic or tropical belt. It is not valid for individual profiles because of the chances are very slim that an atmosphere is in radiative equilibrium because of the water vapor, of the cloudiness, and similar effect. So the next slide is showing how big is the error if you are omitting the dependence on the flux transmittance in the surface temperature computation or the radiative forcing computation. You can see that the surface temperature is overestimated by 30%. The atmospheric temperature is underestimated by 8%, and the sensitivity is about 20% off. And this, what we see here, this is the global average optical thickness of the Earth's atmosphere. So if you are using a linear dependence on the optical thickness, you are just involving this kind of errors compared with the real atmosphere. Let us see the next picture shows that how the new theory is reproducing the observed temperature, thermal structures of the atmosphere. Here, this red line is the Tiger average observations. The dots are the theoretical predictions of the temperature at each level. I am talking about temperature, but it's really a source function, which is pi times the Planck function coming from the Stefan Boltzmann law. So what you see here, the green curve is the US standard atmosphere. It's not radiative equilibrium. It's not a straight line. The dotted line is the temperature curve, what is predicted by the infinite, semi-infinite atmospheric model, together with this surface temperature discontinuity here. So apparently, the new theory is reproducing the thermal structure of the atmosphere pretty well, and then it is reproducing the surface temperature pretty well. Another result is that this dynamical optical depth is a linear function of the altitude. Another interesting result that the new theory can account for the stratospheric compensation, so-called. So if the surface is warming, the stratosphere or the OLR is decreasing, and this curve is just the simulation results, how the full differential of the new transfer function is fulfilling the mathematical requirement, the straight line. The next figure is showing how the new theory is explaining the surface temperature of the Mars. If you are using the true surface upward flux density is this red line. Or transfer function which is coming from the new theory, is giving this black dot. If you are using the energy conservation condition, which is 2/3 of the OLR, then you are overestimating badly the real surface temperature. If you are using the radiative equilibrium transfer function, then you are underestimating these things. So what we can say, this new theory is perfectly describes the conditions both on the Mars and Earth. Here is a summary of our how to say, planetary greenhouse effect study. This blue line here is the radiative equilibrium atmosphere, showing the most efficient cooling of the atmosphere. This thin blue line is the curve of the energy conservation and the hydrostatic equilibrium curve, which is just meeting at the blue curve at the 1.86 infrared optical thickness. And then this is exactly the Earth's optical infrared optical thickness, which is picking up this point. Why? Because at this point, both the energy conservation and the energy minimum principle is working. And then wherever you go from this point, one of them will be violated and the system will go back. So this is why we have on the Earth this. And this is the real meaning of the greenhouse effect on the Earth. The Earth working at full efficiency at a given fixed 1.87 optical thickness, which is at this point. And if you compare with the Mars is working on this dashed line, which is for the thin atmosphere. So you see that the theory is completely matches with the observations. The dots are the observations of the computed from the profiles. These green dots are showing the relative atmospheric upward emittance, which has at 0.5 a maximum, which is quite preferable, and then this is why this point can exist here. Okay, this curve down here is showing the greenhouse effect sensitivity, which is the differential of the transfer function. You see that when you are increasing the optical depth, then the sensitivity will decrease. So if we understand this figure, then we should say that a changing or if you put extra absorbers in the atmosphere, the system will remove water vapor and will return to this point to satisfy the energy conservation principle and then the energy minimum principle. So if you remove water vapor in exchange for carbon dioxide, obviously the climate may change, but the greenhouse effect is still a constant because the system prefers this very spot on this plot. If you want to, I'm late? That's okay. So if we go for the observational point, this optical thickness can be actually measured according to the Kirchhoff law. And here what you see, the measurement of the optical thickness at the Chesapeake Lighthouse BSRN station in the year of 2002 and 2003. The theoretical estimate was, you remember, 1.8 something. Here the average is about 1.9 at this altitude. But what we are talking about, this 1.87 is a global average. So the greenhouse factor could have a kind of meridional distribution, but the global average always must satisfy those two equations to satisfy the energy minimum principle and satisfy the hydrostatic balance and satisfy the energy conservation principle. The next curve, yeah. Okay, let us jump to the conclusions. So what we discovered here, that the downward flux is equal to the upward flux, the surface upward are equal, and then we end up with a general energy balance equation which assures simultaneously the fulfillment of the energy conservation, the hydrostatic balance, and the and radiative equilibrium. For atmospheres in radiative equilibrium, we define the transfer function, which we see that has the most efficient release of the energy from the atmosphere. A runaway greenhouse effect is impossible according to this theory because all greenhouse factors are bounded. Large-scale simulation shows that the Earth's atmosphere satisfies these both equations. The Martian atmosphere satisfies only this equation. The Earth's average flux optical depth is 1.8. The requirements, the theoretical requirements, is 1.86 for the radiative, for the hydrostatic equilibrium, and 1.84 for the radiative balance. Planetary radiative budget studies. Everyone should remember that famous Kiel and Trembert work, which is using the US standard atmosphere to study the global energy budget. That is wrong. That atmosphere doesn't have enough water vapor in it. It is not in energy balance and not in radiative balance. So don't use that. With a partial cloud cover, the Earth system could boot its efficiency to a greenhouse factor of 0.04, and according to the general greenhouse factor, this will be 5/3 of the OLR. Just calculate this. Again, excess of deficit in the global average optical depths will violate either the energy conservation principle or the energy minimum principle. The observed global warming has nothing to do directly with the greenhouse effect. It must be related to changes in the absorbed solar radiation or the other dissipated heat term represented by this PO. And one word about the GCMs. GCMs, you know, a bunch of primitive equations at each grid point. You should not assume that it will represent whatever is realistic on global scale. These GCMs and all the GCMs are conditioned nowadays with wrong boundary conditions. GCM doesn't have greenhouse theory built in. You have to teach the GCM to handle the greenhouse effect. And this is why all those actually predictions of 5 watt, 10 watt, 2 watt is absolutely unrealistic. So shortly, this all. I'm sorry I was a bit in a hurry, but that's all. I'm done.